Hi, my name is John Griffith, and I'm a curriculum developer with the Cooperative Institute for Research and Environmental Sciences at CU Boulder, and I'm part of this amazing team that focuses on connecting the public to the MOSAiC expedition. And so I'm the talking head here today, but I work really closely with Lynn Harden, my supervisor, Anna Gald, and on this particular curriculum that we'll talk about here today, Dr. Jen Kay. I also want to acknowledge all of the funders from National Science Foundation, Department of Energy, NOAA, CU Series, and AVI for their contributions here to this effort. What we're going to talk about today is our effort to bring the MOSAiC expedition and the multidisciplinary study in this multidisciplinary study into classrooms with a high school Earth Systems curriculum. And this curriculum is connected to next generation science standards, where learning is not about memorizing scientific facts, but about constructing explanatory knowledge, where students engage in scientific thinking and move from learning about science to figuring things out through phenomena-driven instruction, and where meaningful, not rote use of scientific practices and cross-cutting concepts are incorporated in everyday lessons. And so with this in mind, trying to incorporate these three bullets here, these principles of NGSS, we elected to construct the curriculum following the model-based inquiry instructional framework, which is a framework designed around the construction, revision, and testing of models by groups of students as they seek to explain natural phenomena. So for this particular type of unit, it's anchored by a complex and engaging phenomena. And by phenomena, we mean observable event. In that first lesson, we introduce students to the observable event and elicit their ideas, meet them where they are. Each lesson that follows provides students with a piece of evidence that helps them explain that anchoring phenomena. And the final assessment is a final model and evidence-based explanation where they bring all of their learning together into these final products. Embedded within all this are the practices, modeling, explanation, argumentation, numerous public records. We make thinking and learning visual, and the learning is collaborative. Lots of working together in pairs as whole group, sharing and learning with and from one another. And with that as the backdrop, I'd like to introduce you to the Arctic Feedback's Not All Warming is Equal. It's a model-based inquiry unit. And what I'd like to say here is that the curriculum includes everything that you might need: teacher guides, student worksheets, PowerPoints, answer keys, supplemental materials. Everything is in here. So I'd encourage you to take a look at the teacher guides. Everything that you will need for each lesson is hyperlinked from those teacher guides. And now I'd like to walk you just through each lesson, what students will be doing and what they'll get out of each lesson and how that relates back to the anchoring phenomena, that is Arctic amplification. In lesson 1, eliciting ideas about a phenomena, students are going to be introduced to the anchoring phenomena, Arctic amplification. So the fact that the Arctic is warming 2 to 3 times faster than the rest of the world. They're going to watch a short visualization showing this warming and work collaboratively to construct initial descriptive models and explanations. So we're basically just going to figure out what they might know already and where they're at in terms of their understanding. Here's an example of an initial model produced by some students, and you can see some of these initial ideas. We've got some different atmospheric gases, melting of ice, perhaps more or less sun, ocean currents. So lots of good ideas. And we're going to try to figure out which of these might help us explain this Arctic amplification process. And so in lesson 2, students are going to identify and describe properties of the electromagnetic spectrum in the context of Earth's energy budget. So the teacher will guide students through a Google Slides presentation, and students will then use what they learned from that presentation to construct a conceptual model using these cutout pieces here. And this is there's also a virtual option here should you be teaching remotely. So students cut these pieces out, arrange them to demonstrate their understanding of Earth's energy budget. We really highlight shortwave energy as energy coming from the sun, and long wave energy as energy or heat being emitted by Earth. And then we put this in the context of this definition of energy budget, really the balance of energy coming in and going out. And by looking at some data sets, this particular graph here shows global temperatures change over the last 120, 140 years. We can see that temperatures are rising, which suggests that Earth's energy budget is imbalanced. So that might mean there's more energy coming in, or maybe there's more energy going out. Some disconnect here. Really, we just want to establish that this imbalance is present. Right? So again, what might that mean? Might that mean there's more sunlight coming in? There's more heat going out? Really, that's where we want to get with this point, just introducing this concept. In the second lesson, students are going to learn more about the greenhouse effect. We didn't introduce that in lesson 2. And to do that, students are going to explore the relationship between shortwave energy, or visible, represented by visible energy here in a simulation, and long wave energy, or infrared energy, heat, represented here. And so students will shoot these different energy wavelengths at atmospheric gases in this simulation, and they're going to watch how these wavelengths, these energies, behave with the various atmospheric molecules. Through this, hopefully students will see that greenhouse gases, or atmospheric gases that absorb and re-emit long wave energy, heat. And then we put that into the larger context. Okay, if we know that heat is absorbed and re-emitted by greenhouse gases, what might happen if we put more greenhouse gases in the atmosphere? And so what we would expect, right, more heat to be absorbed and re-emitted by these greenhouse gases, effectively trapping more heat in Earth's atmosphere, leading to a rise in global temperatures. And so using this simulation and kind of going back to this Earth's energy budget graphic that we introduced in lesson 2, getting students to better understand and appreciate the greenhouse effect. Now, when we think about our driving question, right, why might the Arctic be warming twice as fast as the rest of the world? The greenhouse effect doesn't necessarily answer that or explain that observable event alone. In this figure here, we have temperature anomalies over time. The green represents the global temperature anomaly. So we see global temperatures are rising, but the Arctic is rising much more rapidly. And so while the greenhouse effect is contributing to warming in the Arctic, it's not the only reason, right? There are other reasons why, or mechanisms why, the Arctic is warming more rapidly. So we need to explore those in future lessons. In lesson 4 with Arctic fieldwork, you know, we've just established that the greenhouse effect is contributing to amplified warming in the Arctic, or warming in the Arctic, but perhaps, you know, maybe there's more incoming shortwave energy or more sunlight reaching the Arctic, or maybe there's more energy kind of leaving the Arctic. Maybe that's contributing to the amplified warming. And so in this lesson, we're going to take students to the field sites, MOSAiC field sites, with a Google expedition, an immersive virtual reality tool. We're going to introduce students to a radiometer, an instrument that measures shortwave and longwave energy. And then we're going to have students engage with these shortwave and longwave data sets from the Arctic to see if there's more energy coming in, more energy leaving the Arctic, and how that might relate to temperature. So students will graph and interpret these data sets. And what we see are we have some pretty interesting findings. This black line here represents the amount of incoming shortwave or solar energy. And this dotted red line represents Arctic temperature anomalies. And so what we see is the amount of sunlight coming into the Arctic hasn't really changed over the last 20 years, while temperatures have increased dramatically. And so it's not, we can kind of rule out sunlight, incoming shortwave radiation, as the mechanism driving the warming in the Arctic. But we get some interesting results when we look at the amount of long wave radiation represented by this black line, or heat, that's leaving the Arctic or being emitted from the Arctic. And so we can see that really close relationship between Arctic temperatures in the dashed red line and outgoing long wave radiation or heat from the Arctic over the last 20 years. And so we need to really start exploring this in the curriculum. Why is there more heat being emitted from the Arctic? To do that, I digress. At this point, we take a break. And in this particular lesson, lesson 5, students are going to draw on concepts and evidence acquired during the previous lessons to revise their initial model. So this is an opportunity for students to reflect on what they've learned and update, again, revise these ideas, these explanations that they have for the phenomena of Arctic amplification. So you can see in this one, we've got some examples: temperatures increasing, human activities, fossil fuels. We've got some greenhouse gases in the atmosphere. And so lots of good things being added to these revised models. In lesson 6, again, we're going to start exploring why it is that there's more heat being emitted from the Arctic. And to do that, students will engage in a measuring albedo lesson where they'll use a reflectance app to measure the reflectance or albedo of different colored surfaces and come up with a rule about the color of a surface and its albedo. And students will come to understand that lighter colored surfaces have a higher albedo or reflectance than darker colored surfaces. And then students will take what they've learned and apply it to a short activity where they'll put ice under some sort of heat source, light source, or even outside in the sun. The ice will be on a dark surface representing the ocean and a light surface representing the ice, and measure the rate at which those ice cubes melt. And ultimately, students will discover that the ice on the darker colored surface melts more quickly, which suggests that energy from the heat source representing the sun is being perhaps absorbed and causing the darker ocean in this case to warm up and melt ice more rapidly. So again, engagements designed to think about, okay, why might there be more heat being emitted from the Arctic? In lesson 7, we have students we introduce students to the concept of the Ice-Albedo feedback. And to do that, students are going to analyze maps to calculate and compare changes in the Arctic's albedo. So students will calculate the albedo of an Arctic with lots of ice and the albedo of an Arctic with less ice. And so of course, the albedo of the map with more ice will be higher. There will be more energy being reflected. And so what students will draw on what they learned previously in lesson 6 to say, well, okay, more of the energy going into this map here with less ice will be absorbed, probably resulting in an increase in temperature, driving more melting. And so through these engagements, we want to introduce this ice-albedo feedback where rising temperatures caused by an enhanced greenhouse effect are causing sea ice to melt. That's decreasing the albedo or reflectivity of the Arctic, which is exposing more of the dark ocean. More heat is absorbed, which leads to further ice melt. And so this positive feedback loop continues. In lesson 8, we're going to have students test these ideas, test their models by matching their ideas against real world data about the phenomena Arctic amplification. And so these are data curated by MOSAiC scientist Dr. Jen Kay. And what we have here is albedo represented by the black line here, with sea ice extent represented, basically the amount of sea ice in the Arctic represented with this dashed line over the last 20 years. And you can see there's a really close relationship, which we would expect, right? As sea ice declines, so too does the albedo, does the reflectivity. As the amount of sea ice increases, so too does the albedo. And so again, we're using data to test our claims, to test our ideas. And there's a really important reason why we introduce the driving question with the term, why might the Arctic be warming twice as fast as the rest of the world? Because it's still something we're studying. We have students in lesson 8 also create a scatter plot looking at the relationship between Arctic temperatures and Arctic albedo. And if it was albedo that was driving the Arctic temperature anomalies alone, we would see a really tight relationship here. And while we do see a relationship with increasing albedo, increasing reflectivity, we get reduced temperatures. We do see that relationship. It's not as tight as we might expect, which suggests that there are other factors contributing to the amplified warming in the Arctic. And now's a really good time to ask students to consider, well, what other factors might come up there for you? Things like ocean currents, atmospheric currents, changes in those two things are ideas, maybe permafrost, some things that students have come up with in the past. And now, given all of these lessons and all of this evidence that students have acquired, their task now is to put their new understandings to the test by creating their final models. So in lesson 9, the final model construction, students are going to work in pairs to draw on concepts and evidence to construct these final models. And so we'd expect to see students talk about the greenhouse effect and how increasing concentrations of atmospheric greenhouse gases are absorbing and re-emitting more of this outgoing long wave energy. We'd expect them to link that enhanced greenhouse effect, this warming, which is driving the melting of sea ice and triggering this ice-albedo feedback. And so we've got a high albedo initially, an enhanced greenhouse contributing to declining ice. With declining ice, the albedo decreases and more heat energy is absorbed by that exposed darker ocean, and that feedback continues. So a really nice conceptual model here. And last, students are tasked with working independently to write an evidence-based explanation for this amplified warming in the Arctic. And we expect this explanation to have the story of what happened, important science ideas and concepts, and then any evidence that they could refer to throughout the course of the unit to be included as well. And so we're really proud of this unit. We've got about 100 teachers testing it out this school year, reaching thousands of students. And we're excited to continue to reach other classrooms, other students with these materials. And so while the fieldwork portion of MOSAiC is over, the science is just beginning, and so too is our work here with series education outreach. And so we're excited to continue to work with anyone and everyone who's interested in learning more. I've got my email here. So please reach out to me if you have questions or comments, and look forward to working with you.